Section 9.3 was applications and probability. We talked about one application of probability last time. That application is odds. I normally ask where you've heard the words odds used, and I forgot to do that. Where have you used or heard the phrase the word odds used before in reference to what kinds of things? You've never heard it? I don't believe you for a second.
That game, it's like, what are the odds?
A game? Any specific games you can think of? I mean, like I gave you some examples of rolling dice and stuff like that, so gambling is definitely one of them. Gambling like casinos in general. Any others? Ashley?
I was thinking like cornhole.
Cornhole? Do you guys I'm not familiar. I mean, I know what cornhole is, but I'm not familiar enough with the rules of the game to know. So odds are used in cornhole. Okay. Sometimes people think of horse racing. For whatever reason, people think about probability more with casino games and odds more with horse racing. I'm not really sure why. You'll sometimes hear odds also used when you're talking about playing like games with skill, like football games. What are the odds that a team will win versus another team will win? Basketball, stuff like that. Nobody's going to tell me Hunger Games? That's the one somebody usually tells me. Nobody's going to tell me that one, huh? Okay. So odds are used quite a lot, but they're usually in reference to like what AK said sort of as a general statement in terms of some kind of games, some kind of a competition. The other application we're going to work on in this section is called expected value. Expected value is the expected outcome if you do a game enough times. So we're going to give a scenario. So if let's say we have possible outcomes of an experiment are A1, A2, all the way up to AN. So you can have a bunch of outcomes. Each of those outcomes has its own probability, P1 up to Pn. Then the expected value is A1 times P1 plus A2 times P2 all the way up to AN times Pn. So this is a specific equation. It's going to have numbers, right? So my outcomes can't be, red or blue, boy or girl. That's not the kind of outcomes we're talking about. It doesn't make sense in this context. So a really nice example would be something with a dice or with flipping a coin, but we'll use dice because that's a clearer explanation. If you're rolling a dice, the outcomes are either 1, 2, 3, 4, 5, or 6 if it's a single die, right? Sure. And then depending on the outcome that happens would actually depend on what you would have happen to you. So maybe you roll the die on a certain number, you get $2, and on another certain number, you lose $5, okay? Those would be the values of the different rolls. So if you do it with coins, you can do the same thing. If I flip a heads, I get $5. If I flip a tails, I lose 10. Those kinds of things. Those are the expected values. Now the probabilities are the likelihood that each of those events would happen. A fair game is a game where the expected value is 0. So, whatever the expected value is at the casino, it's not 0. Because they built a building and they hired people, right? So it can't be a fair game. Now you may win sometimes if you go and you play a game, but it can't be a fair game by definition, or they wouldn't have the money to build the building and to supply, all the things, okay? So those are not considered fair games. So let's actually do an example, and it is a casino example, maybe one that you're familiar with, maybe not. On a roulette wheel, there are slots numbered 0, 0, 0, 1, 2, 3, all the way up to 36, okay? So it's a wheel, like when you spin it for the game of life. Okay, it's a wheel, but it has 38 different slots, right? Because it's got 1 to 36, 0, and 00. One way to bet, there's lots of ways to bet, but one way to bet is to actually bet on a single number. So you say, I think it's going to land on 5, okay? If the ball lands on your number, then you receive 35 chips plus the chip you played. Okay, so you give them 1 chip. If you win, they give you your chip back plus 36 more. 35 more, so for 36 total. Okay, and if you lose, they just keep your chip. So the first question, part A, says, what is the probability you will land on 00, and then that you will land on 0? So what's the probability that when you spin the roulette wheel, it lands on 00? 1 out of 38, absolutely. And what's the probability that it lands on single 0? 1 out of 38. Okay, so far so good? That's just probabilities. Notice we are, in fact, using probabilities here, not odds. This is not an application of odds. It's an application of probabilities. Okay, so I love my father-in-law. He is an absolutely incredible and amazing person. But this is one of the things that I look at him and I go, huh. So, when my father-in-law passes a roulette wheel, my in-laws will occasionally play games like on a cruise or something like that. That's the kind of, and they spend a little bit of money and they've got enough. It's not an addiction. I'm not advocating that you go gamble. Please don't mishear me, okay? But my in-laws do occasionally play games. So if you've ever been through a casino or whatever, they actually have a board up by the roulette wheel that tells you what the most recent spins have been. It'll tell you it's been a 3, and then it's been a 7, and then it's been a 3 again, and it's been a 5, then it's been a 0, and then it's been a 12, and whatever. It tells you how far back, I don't remember, but it goes back a few ways. And so when my father-in-law passes one of those boards on a roulette wheel, if he sees that it hasn't hit 0 or 00 on that board, he'll play the game. That's his decision. He actually will bet on both numbers, okay? So he'll put a chip on the 0 and he'll put a chip on it landing on 00. So if he bets one chip on each number and the chip is worth $10, what is the expected value of his bet? So in his scenario, we're looking at expected value. We have the possibility that he, we have the value times the probability. There's 3 different things that could happen. I'll write them out that way. Value times probability. This is just the expected value formula in words. The value times the probability. Okay, so there's 3 different things that could happen. It could land on 0, right? I mean, like it could. It could land on 0. So if it lands on 0, we know that the probability of that happening is 1 out of 38, correct? Yeah. It could land on 00, and the probability of that happening is also 1 out of 38. Those are both scenarios where he wins. And it could land on one of the others. So how likely is it that it lands on something that's not 0 or 00? 36 over 38. Okay, so far so good. Those are the probabilities. Now let's go back and do the values. Okay, so each chip's worth $10. Okay, and he's bet 2 chips. So how much money has he put in? He's put in $20. If he wins, how much money does he get back? $360. Izzy, explain where you got $360.
He gets 36 chips, so 36 times 3.
Yeah, he gets 35 plus whichever it actually landed on that was actually his. So he gets 36 chips back, actually. So he would get $360. Does that make sense? But he paid $20 to do that, right? So he doesn't really get $360. He gets $350, right? Because one of those chips was because he bet on the other number that didn't work out. So he'd actually get $350. So far, so good? And that's the same thing that happens whether he lands on the 0 or the 00. If he lands on either of those, he gets $350 because he gets $360 back, including the chip that he played, and he lost a chip in the process that they kept. Okay. Over here. What about if he gets one of those other numbers? What happens? He doesn't get the 360. What does it cost him? $20. So the value, sort of like the net change in his wallet, would be a negative $20. He lost 20. That's why it's negative, right? Negative. So we're going to calculate this. We're going to see what happens. We have 350 times 1 over 38, and all the way down. All right, so 350 times 1 over 38. I don't know. You're going to grab your calculator. I'm going to grab mine too. And this is money, so 2 decimals seems to be reasonable, right? So each of our answers, we're just going to record to 2 decimal places, and we'll add everything up at the end. So we have 350 times 1 over 38. What is it? 9.21 And the next one will be 9.21 because it's the same thing. And then I need negative 20 times 36 over 38. And what do we get? Oh my goodness, I made a mistake. There we go. I think I'm back. What was it?
18.95.
Fabulous. 18.95. Okay, so we're going to add these together. 921 plus my 921 minus my 1895. And what actually ends up happening? Negative 0.53. So if you play the game enough, it's not a huge loss, right? I mean, you have to hit some point in there, but for this to actually work out, of course. But it's not a huge loss, but on average, you would lose 53 cents every time you played the game. Okay? So it's an average loss of 0.53, right? A $sign 0.53 for each play. It's not a very fun game. You don't really get to do a whole lot. It's not like when you're playing cards and there's any strategy or anything like that. You just choose a number, and then it either hits or doesn't. But that's the way this game would work. And your average loss would be 53 cents for each chip you bet. So when he bets 2 chips, he's got an average of actually $1.06 he loses, right? Because he bet 2 chips instead of just betting 1. But for 1 chip, it would be a loss of 53 cents. All right, let's change. So it's not a fair game also. You can see that because it didn't get 0 at the end. Can't be a fair game if there's no 0 at the end. All right, let's do another television, do a television game show. This is a little different kind of a question because it's asking us something slightly different. In the television show Deal or No Deal, are you guys familiar with the show? Okay, great. If you've been to like Dave & Buster's or Chuck E. Cheese even, they got Deal or No Deal machines there. I don't know if you've ever seen those, just so you know, they do. They're a lot of fun, my kids love them. In the television show Deal or No Deal, a contestant is down to 2 cases with equal probabilities of being chosen. The cases have $250,000, $10 in them. If you're the banker and you want to give a reasonable offer to the contestant, but not too lucrative of an offer, what kind of deal would you offer and why? So, you know, the little banker that you can't see, you only see the profile or whatever's going on with the screen, yeah? You're that guy or that girl, and you're making that decision. And the decision is being made with probabilities. I mean, that's how the decision's made. So the actual kind of probabilities are expected values. So there are 2 cases, so there are only 2 possible outcomes. One outcome is that you get the case that's $250,000. That's the value of that case. The other outcome is that you get the case that's $10. So those are my 2 cases. And it says the probabilities are equally likely. So what are the probabilities of choosing either case? 1/2, or you can do 0.5. So yeah, it's a 1/2 probability that each different case will be chosen. All right, so if we do half of $250,000, it's $125. And half of $10 is $5. So the expected value is actually $125,005. Okay, so that's actually the expected value. So the expectation is that if they had this happen enough, half the people would get the $250,000 case, half the people would get the $5 or $10 case. It would even itself out over time to being $125,000, give or take. So we need to answer the question though, because that's not really, I mean, that's all the math that you go into, but you're not the banker telling them the math, right? The banker just says a number. So our answer needs to be something like this. You'd offer around $125,000. If you want to say $125,005, that's fine. But I'm kind of talking about an approximation here. They usually don't offer weird numbers when it gets up that high, like ending in a funny number. Definitely no change. $125,000 Slightly, you could leave your answer at that, but I'm just going to sort of make a note here. Slightly more would be better for the contestant. Slightly less would be better for the bank. And of course, they're also weighing out dramatic appeal with the audience, right? That's part of it too. But numerically, this is actually what you would be looking at. The answer needs to be, it's around $125,000 that you'd be offering to make it a reasonable estimate. Any questions on that one? Okay, one more type of expected value. We're going to look at a lottery. In a given lottery, we know that the odds of winning the lottery are 55 million to 1. Be really careful when you see words like 55 million. Make sure that you understand that that's 55, with lots of zeros after it, right? My husband was wearing a shirt just yesterday, and it's an adoption-related shirt. It actually says, it was some people we knew who were adopting 2 kids, and it says, it was an orphan shirt, and it says 143 million minus 2. And so, trying to trick my kids up, because that's the kind of mom I am, said, what's 143 million minus 2? And the expected odd answer that they should have said was what? Do you know? Do you know what people say all the time? What's 143 million minus 2? 141 million, right? Because they forget about the word million. That's why I'm mentioning it here now. Remember that a million means you got lots of zeros at the end. But my kids didn't even get that far, so it doesn't matter at that point. But just keep careful for yourself, because we're going to need that 55 million all written out with all the zeros here in a minute. Okay, first of all, what is the probability of winning the lottery? One over what? 55 million, 1. Remember we talked about odds last time? One person wins, 55 million lose. So there was 55 million and 1 that would have played the game. Okay, it doesn't change the values all that drastically, but it is really 55 million 1 for the probability on that. All right, so on part B, it says if the grand prize is 14 million, again, that means 14 with the 6 zeros, and the tickets cost $5, is the game fair? Well, when you buy the ticket, there's only 2 possible outcomes. What are they? You win or you lose. So we're going to do an expected value, and it's going to be the value that we win times the probability that we win. And we're going to have the value if we lose times the probability if we lose. So each of those values, of course, are different. I've kind of shortcutted how I've written it down, but they're the value of those things happening. Okay, so let's look at winning. If you win, how much do you win? 14 million, or do you? It'd be 14 million minus 5, because it costs you $5 to play, right? And that's not 11 or 9 million, right? No, it's not 9 million. Okay, so we have 14 million. Here's my 14 million number. So I would actually win 13,999,995. Okay, does everybody follow where that weird number came from? Because it's a weird number, right? But you had to pay $5 to play. This is assuming, of course, you bought 1 ticket, the way it's set up. What is the probability that you win? 1 over 55 million, 1. Yep. Okay. What's the value if you lose? -5. It's not the end of the world, but I mean, you could have gone to Sonic like 3 times. Got a drink. Just saying. All right. And what's the probability that you lose?
55 million over 55 million.
Yep, it's 55 million over 55 million 1. I'm going to shrink this just a little bit so I have a little bit more space. At least I think I'm going to. Here we go. All right, so I have 55 million, because there's 55 million people that played that didn't win, over the 55 million and 1. Okay, so again, this is assuming that one person wins. I know that's not how it always works with the lottery when you get to choose your own numbers and so forth. I get that. But we're kind of downplaying it to a little bit more of a simplistic look, all right? Everybody good? So one person wins or they lose. So for an individual. All right, so grab your calculator because these numbers are really big. 13,999,995. Let's keep 3 decimals just in case things add up funny. So for right now, I've got 0.255 on the first one. And I have negative 5 on the second one because it's 4 with a whole bunch of 9s. Did you get a whole bunch of 9s? Mm-hmm. Good. And if I take that value, so my -5 and my positive 2.55 and round, I have -475. Right, rounding with 2 decimals because we are talking money here. A lot of times with expected values we're talking money. Don't have to be, but we are a lot of times. Okay, the question actually didn't ask find the expected value. But we needed to find the expected value in order to answer the question, which was, is the game fair? And the game fair doesn't mean I like the game, I don't like the game. This isn't the kid whining and saying, but that's not fair. It's not fair like that. There's a mathematical definition we're going with here. Is it fair? And the answer is no, it's not fair. Why is it not fair? Yeah, no, because the expected value, that's that capital E, does not equal 0. So it's not unfair because we won or because we lost. It's unfair because on average, the expected value we're getting is not 0. So what's actually happening? So let's look at the next couple of questions. Part C asks, or says, as with many state lotteries, the proceeds are often said to benefit education. Have you heard that before? Okay, just checking. Under these conditions, if all proceeds benefit education, and 1 million tickets are sold, what is the expected value from the lottery sales? So let's go back and talk about what this number over here actually meant. -4.75. Okay, so this was all done from the perspective of the person buying the ticket. So on average, I expect every time I play this particular game with these particular, constructs in place, that I will lose $4.75 every time I play. Make sense? Okay, so if I'm losing it, somebody's gaining it, and according to C, a lot of times that's supposed to be education that's gaining that. Make sense? So if I play the game as a consumer, then education gets $4.75 from the sale of my ticket, and the sale of all the tickets, which is how many tickets in the problem? A million tickets. So if you take the 1 million times the $4.75, what do you actually get? What is it?
4 billion.
It's still millions. 4,750,000. So $4.75 million. It's a lot of money. Okay? On average. But remember, expected values are averages over time. All right? Over time. So if the lottery plays one time, you're expecting that you're going to average over the course of playing the lottery a whole bunch of times $4.75 million. That's great. But those aren't the real outcomes of what's going to happen here. What are the real outcomes? Well, there are two real outcomes. One real outcome is that no one wins. And the second real outcome is that someone wins. Right? Yeah, I mean, either someone wins or they don't. So let's talk about the no one wins scenario then. If no one wins, then they didn't actually, the state that is, or the lottery system, did not actually collect $4.75 per ticket. What did they collect? 5. The tickets were $5. So if no one wins, then there was really $5 tickets that were sold, and they sold 1 million of them. So how much money did the state make? 5 million. And that's not dreadfully different looking. Wow, that was too many zeros. That's not dreadfully different looking than my 4,750,000. I mean, not that 250,000 is nothing. I'm not saying that. But the numbers are not dreadfully different. However, if someone wins, things look quite different. Now, the state still took in $5 million, right? But if someone wins, what happens? They lose 14 million. You got it. They lose 14 million. Which means what actually ends up happening is that there is a negative what? What's 5 million minus 14 million? Close. 9. Negative $9 million. Those are the real outcomes, not the on average outcomes, but the real outcomes of playing the lottery system through with those constructs one time. So I bring this up because I want you to sort of be on the lookout for things that sound like they're benefiting things they really aren't. People do stuff with numbers all the time to mislead you. We're going to talk in Chapter 10 a lot about misleading with statistics. So a lot of misleading with statistics that happens every day. I want to say especially now, but really all the time. All the time there's misleading with statistics going on in your lives, and you don't always catch it. I don't always catch it either. And so just something to be aware of. On this one, you're sort of led to think, well, this is a really good thing. I mean, like, education's benefiting. And of course, we all would love education to have more money and to benefit. That is a good thing, right? But you're saying then that you want these people who are paying this money to just lose too. I mean, is that really what you wanted? You wanted all the people who are doing this, who are hoping to win, to lose? Because that's what you have to do. You have to hope they all lose, otherwise education doesn't win. That's the way those numbers work out. And it's a really funny scenario when you actually start looking at it. Now, just as a word of interest, not because it's mathematically a part of what's going on, but what will usually happen if you do win a big sum of money like that is they don't give it all to you at once. Did you know that? Has anybody ever known anybody who's won something, whatever? They will usually pay out to you over a period of time. So they're not, bankrupting the education system if that were to happen, just FYI. They pay it out to you over a period of time, or they'll offer you a lump sum amount that is considerably less if you want it all at once. That's actually the way it works out, because otherwise you would have a problem. This would be a big deal, right? You only played the lottery once, and all of a sudden now all the money that was promised is actually a negative, and we got a big issue. So that's how they sort of mitigate that issue coming up, is the way that they pay out their winnings when it happens. So, all right, so we are done with section 9.3. You have 3 homework problems, or group work problems, to take a look at before we head out today, so we can go ahead and get a look at those.